Think we'll get started here. All right. Welcome everybody to the third research presentation in our cyber infrastructure symposium here at University of Hawaii. It's a pleasure to introduce Dr. Kai Yang, a researcher in astrophysics and currently a research scientist at the SETI Institute. His journey spans three different continents, beginning with a PhD from Nanjing University in the School of Astronomy and Space Science in 2018, followed by postdoctoral appointments at the University of Sydney, and just recently here at the University of Hawaii Manoa in the University or in the Institute for Astronomy. So today he's going to be presenting some of his research, a novel physics-informed machine learning method for 3D solar photosphere reconstruction. So yeah, let's give everybody give our attention to Dr. Yang.
Oh, thank you. Thank you, Shane, for the introductions. Hi, I'm Kai, and I'm from Mānoa, and I'm so sorry that I cannot be there in person. And and thank you for the invitation to give this talk on our research. And we just recently developed a very new technique, and we indeed applied it to some most advanced observations and found some result, and we want to share about that. And then this is the sun, and as we know that for those who are not clear about what the solar physics is, well, the sun actually it is the source for most of our solar system digesters. It causes a lot of problems for our space weather, and not only for Earth but also for all the planets in our solar systems. And it happens from the different spatial scales, from the very tiny one, like this, it's just about several hundred kilometers scale, space scale. But I also go to the stellar scales. We can see some blast eruptions from the solar surface into the space, and can go such kind of thing can propagate through the entire solar system. But all of those phenomena, all of those activities, eruptions, they all have the energy resource from the surface, the photosphere that we can observe by our naked eyes. But I do not recommend do that, but that will do harm to your eyes. But I mean, that is where the source came from. Those dark regions we call sunspots, is they are dark because they're color. They're color because there are very strong magnetic field over there, which was first identified about 100 years ago by the Siemens platings. And that is also the sunspot is also the first object that we can identify that with the magnetic field outside of Earth. And then in order to observe such thing and study such kind of phenomenon, what's the physics behind them, we need a lot of instruments. We need the instrument, not only the space-based telescope, but also ground-based huge telescopes. And well, the Hawaii is one of the most best site for the observation for observe the signs on our Earth. And indeed, we now have the best solar telescope in on Maui on the Halakala Summit. It's the best. It's the one of the most, no, not one of, it's the most advanced solar telescope, and the it's the next generation solar telescope. Not oh sorry, not the next generation. It's the generation, the only one in the current generations, and it can provide not only the spectral of the light, but also the polarized spectral of the light. We know the light, it does not only have different colors, we name it a spectral, but also it has a different kind of polarized mode, like it shown here. And the decades just observed different the different polarized mode for all of those different spectrums to get a complete ensemble of the observations from the sun, because the decays that have very huge apertures, about 4 meters. I mean, that's the largest in the world for the sun. So it can capture a lot of light signals very efficiently to have a high accuracy in the spectral polarimetry of. And then and it provides about 10 terabytes per day. It's a pretty huge data set, and we need to precise those data sets to give a sense analyzed related set to our scientists. So in that way, we can not only read the information from light, but also learn the information behind it. We mean the physics behind it. But one problem occurred is that in the traditional things, once we observe the spectrum and we do the traditional inversions, pixel by pixel, all the physical informations need to be sampled on the so-called optical depth. It is an integral of opacities along our line of sight. It does not give us a sample on the real space. So one problem that comes out is that the final 3D data set we have is only have 2 dimension in space, but one dimension is the so-called optical depth. So that make it difficult for the post analyze, because we cannot easily take the spatial derivatives to obtain any further variables like electric current or Lorentz force or any other related variables. But those variables are very important to analyze what happens in those activities, and that provide energies. So the goal of our project is to make a modern state-of-the-art technique that we can translate the spectral polarimetry observations to the real three-dimensional physical wobbles in the lower solar atmosphere, that we want to translate the light to like temperature, pressure, Doppler velocity, and magnetic field parameters in the real 3D. But there are two major problems that we met. One major problem we calculate as 180-degree ambiguities in the azimuth angle from the inverted magnetic field. Such problems is naturally inherent from the quantum transition. So physically, we cannot solve that from the simple physics ways. And the other problem is that we calculate a Wilson depression. This phenomenon was observed about 200 or 300 years ago, because that we can see that the surface we see in the center of the solar sunspot is deeper than the nearby quiescent regions. It is due to the specific region of the temperature is different. So this is just an apparent effect, but it causes the problems on reconstructing the 3D structures. That is here as illustrated here. The optical depth we have, it's just that they gave a regular 3D data cube, but in the real 3D, it's a corrugated surface in the lower atmosphere. So that's the two major problems. Well, to solve that, we use the most currently developed method, and we name it as a Haraka disambiguation. And it solved this problem. This solve the reconstruction problems by solving these two problems I mentioned above. And also it solves some problems that were made in the previous machine learning techniques. Usually we train the model we trained by a pre-prepared simulations will always predict a simulation, that simulation-like solution. But if we lost something in that simulations, maybe we lost the at the final solutions, and that will lead us to a misunderstanding of the physics behind it. Usually, the traditional way to solve these problems is to train your data set, your model with a data set that covers the large parameter space, the larger the better. But and also another thing, another aspect is to apply a target data independent approach, such as what we used, the physics informed method. The key ideas here that we solved everything here. We call it the divergence-free equation. That is the nature of the magnetic field. Since till now, we did not get any magnetic monopole in our universe, though some theoretical physicists claim that they could make some quasi-particles in their theories, or some experimental physicists they do that in the condensed matter, but they are not the real particles. We are fundamental particles. They're just the quasi one. So that makes us believe that till now the divergence-free equation of the magnetic field still hold and strongly hold through our universe, and also include the sun. So the basic idea is that this equation, what it tell us? It tells us that if we have a small cell structure so there, the total magnetic flux across the entire cell, the closed cell surface, should be zero. So we, based on this idea, we can imagine if we could have something that shift the relative positions of the eight node, and then finally adjust the 3D geometry to give a geometry scale that minimize the total magnetic flux across this cell. So in that way, we could obtain a final solutions that both obtain the divergence-free equation and also the inversion problem. But this idea is just a very basic, very basic ideas here. We only show the problems with only 8 nodes here. But what is in the real observations? Usually, in the real observations, we have about 10 to the about 1,000 of pixels in each dimensions, and about 30 samplings in the optical depth. And also consider about the disambiguated problems for each node. We have two choices for the azimuth angles inherent from the magnetic field ambiguity problems. So each node we have two choices, and in realistic observations, we have about 30 times about 30 million pixels. So what's the final options we could have? We have 10 to the 10 to the 7 solutions, and we should pick up one solution from such huge possibilities to find the global minimal solutions for reconstructing such 3D problems. And this possibility is even larger than the total population of the electrons in our observed universe. So in the traditional techniques, it seems a little bit impossible, but actually now we can make it be possible. The technique we use is so-called neural operators. It maps the magnetic field, the ambiguous magnetic field, to the realistic magnetic field and a realistic geometric scale. But how to train it? The training side is pretty tricky, and it only depends on the equations of the divergence free. And we have designed a very specific numerical scheme to calculate that. That is a true technique, so I will not present here. Now let's move to the validation about this technique to see how good it could be. We validate it with the relative magnetohydrodynamic simulations that mimic the realistic simulation, realistic conditions in the small scale solar granules. And here is the result. We can compare the predictions of the geometry scales from our model and the ground truth, because it's from the simulation we have the ground truth. We simulated three different typical conditions on the sun: the quiet sun, the plage regions, the sunspot regions. And as you can see here, this is the 2D histogram, and the color is in the log scale. And then we can see that most of the pixels just fall on the identity lines here that indicates our model can give a very good predictions when compared with the ground truth. And it only depends on the training of the physical laws, not a target data set. And then since we have the realistic three-dimensional magnetic field and the geometries, then we can do the spatial derivatives. So we could have the magnetic field. So we could have the electric current, vector electric current, and the vector Lorentz force. While in the traditional things, it can never have the vector 3D Lorentz force for the photosphere, and this is the first thing that we can do, and give dynamic independent computations here that should make us to that provide us a very powerful tool to investigate the things previously impossible. And this is the validation of about the accuracy here. And we also have another advantage is that it also have a very good generalization capabilities. If we compare the result angle from the truth and prediction, we see it's a very good. They sorry, they give a very good solutions. And well, the dashed bright box indicate the real training site, while the margin regions is not trained, is not optimized in our technique, in our training processings, but it still gave a very good predictions, though somewhere it's not that kind of good. And because our training is limited to very small data size, but it still shows as a strong capability for the generalizations to the unseen data. So now let's move to the realistic observations. And then in the realistic observations, we can take data from the Daniel K. Noel Solar Telescope. This movie just give us an imaging observation from the VBLIs. And since the decade is a large aperture telescope, ground-based, so its a field of view could be very small. As we compare the global sun that is captured by the space telescope, it's a resolution. The space-based telescope's resolution is pretty larger than smaller than what we can have in the ground-based. And here I just give you the field view of what the different instrument we have from the decades. And then this is indeed the real observations we use for our techniques. But here we can see some projects, we can see some few numbers here and some strong magnetic poles over there, and the spectral, the polarized spectrals give us the informations they have a strong magnitude over here that they show the the Zeeman splittings. We can even see that from the Stokes phi parameters. Well, with the traditional inversion techniques, we can obtain the magnetic parameters and the Doppler velocities on sampled optical depths. Well, actually, we have a series of optical depth samplings that from the log10 to from 0 to about 5, or -5. And log10 0, log10 0 means the normal solar surface that we can see by our naked eyes here. Well, if we take a small field view, because our new technique applied to the training data set, we just want to have a quick test to see how the technique can work. So we take this rather small field view. And it contains both the strong magnetic field in a small pore, but also the quiet regions with some granular structures here. And let's see what's the 3D solar photospheric magnetic field lines. And I have to say, in the world, this will be the very few people have saw this before from real observations. Let's see here. Well, the background surface is just one selected optical constant optical depth value that I show you how the corrugate surface of the optical depth that I mentioned, that I mentioned several slides ahead, and that the Wilson depressions looks like. Well, the color field lines indicate the magnetic integrated field lines, and the color is the magnetic strength here. And you can see a lot of magnetic fields just merge from the bottom to the top, and all span from the bottom to the top. This is the detailed structures in the very thin very thin layer of the photosphere that just gave about several hundred kilometers thickness. So here we get a very detailed structure of them, and now we can see the real 3D vector electric current associated with the 3D model. And again, we take it to show the background surface as the same as the last movie, and the arrows here indicate the electric current magnitude. Well, the units here is just a unitarized system. I didn't convert it to the physical unit, but you can still see that most of the electric current just follow the right hand row. It's just the result of the Ampere's law that if we have a magnetic field vertically, that the electric current should follow the right hand, and because it's the electric current is the curve of the magnetic field. And then how can such kind of electric current and magnetic field contribute to our studies on on the solar activities here? And then this is what I will talk. And from the field view here, and we have some high cadence of filter imaging observations from the decades as well. It captured CASM 2K observations. Well, these observations it captured the features slightly higher than the photosphere, but they share some common magnetic root. And we can see a lot of small jet or here, and a lot of activities here. Though you may see sometimes the movie is blurred. That is due to the scenes of the actually the Halakha summit. But we can pick some very good scene conditions to check what happens over there, and we pick several several different small scale jet happened over there. And if we zoom in, we can see such kind of a strong. I just use a reverse color map. So the dark, the strong of those jet-like structures over there. Well, if we carefully call along the image coordinate systems and with the different instruments, and one jet here we see is gave structures here, and it gave a very thin elongated fiber-like structures. And if we trace the magnetic field from here, it gives us in this way. I mean, it's not perfectly matched, but I mean, that's the best we can do. And if we take a look about how the 3D structures over here, well, the colors, and this is the magnetic field lines, and the color indicate we called the twist parameters. The stronger the twist means it just the field lines just swing heavily, and we can see that from the view that the magnetic field is merged from bottom to the top, and in the core region of that, there is a strong twist of the magnetic field lines. Such kind of merged structures in the solar physics, we name it as reverse canopies. This structure is always studied in the theory and in the theoretical and compute and the simulation part. It's rarely observed in the way like this from the real observations. This structure are always thought to be a very good place that the magnetic field reconnection could happen. That is a precise the magnetic field released energy into the heatings and the particle acceleration and a lot of spark and radiations. And most of the previous things of such just happened in the simulations, but now we have an opportunity to see it in real observations. And it's not only one case, actually, though I only show one case here for such structures, but also have a lot, we have a lot of samples in the data site. Well, another example of the jet, this one. If we trace the magnetic field, we can see the structure in this way. If we take a 3D visualization, well, we can see the magnetic field goes vertically in this part, but it almost touch and turn its orientations and go to and touch the surface and then goes back to form an arc-like structure. The tricky thing is that the region that they touch the bottom, how they touch the bottom. This touch this touch site is also theoretically predictate a region that magnetic field reconnection should happen. And we indeed saw that in the solar coronal regions, in the higher chromospheric regions, but we never imagined such a kind of things indeed happened in such a thin photospheric regions. The entire 3D structures I show here is still in the photosphere within about several hundreds of kilometers. I mean, several hundred kilometers compared to our Earth is a long distance, but in the solar photosphere, it's just a tiny. And usually, many instruments even cannot resolve such uh, tiny structures. And so it seems like it indicates that the something indicate that the such structures not only responds to the strong magnetic eruptions, but also for the tiny one. So they could be a candidate that responsible for the so-called solar heating problems that last for about 1 centuries, and a lot of theories have discussed about that, but we never have a real way to touch the realistic observations in the real three-dimensional way. And here is a summary of about how the technique works and how the science we found. And I just want to emphasize that most of the things works under the physics-informed neural operator ways rather than the target input and target data pair ways. So it's not supervised, so we can trust the solution because the physics equation is satisfied. And that is what we want. I think most physicists want to know, because in this way, we do not have to interpret the machine learning models. And the only thing we focus on is the physics. And also, the DKs provide very unique ways that we can work than any other telescope before. And at the finals is a summary about how the model works. Currently, we developed the model with two V100 GPUs, and for each demonstration case, we run for about 8 hours. Though it looks short, but actually we run more than that for optimizing the model architectures and fine-tuning the hyperparameters. And also, the cases was around for around 24 hours only on selected region, not the entire field of views. That's because the model already have a very good generalization capabilities, and only selected typical regions could enough to train the neural network. And at finals, I have to specifically thanks to Mr. Stanley Cordot, that is our IT managers, that helps a lot on located GPU instrument and handles on a lot of management on those computer resources and collaboration with the core HPCs over here, and now the clusters runs pretty good. And that's all for my talk. Thanks.
All right. I see we got some applause here. Thanks, Dr. Yang, for this very interesting talk here. Are there any questions from the audience? I have a question. Dr. Yang, I see you ran some of your demonstration cases here for your summary
Mhm,
slide saying using V100 GPUs. Do you think
mhm.
that your runtime would decrease on um, like A100s or H100s or even some of the new Blackwell infrastructure?
Oh, yeah, definitely it could be. And indeed, I'm also developing the next generation of this model on the H100, and indeed it can reduce a lot. But if you have more resources, you will always think maybe we can make the model more heavily to handle more things to make the model more larger. And if we increase that way, the time goes up again.
So I guess yeah, as you're talking about scaling, what kind of increase in time do you see? Like if you double the scale, like
Actually,
double the time. Or...
I didn't check that carefully. Sorry.
Oh, no, I was just curious if you had a guess.
Oh, yeah, no.
Okay. All right. Okay. Does anyone else have any
Okay,
follow-up questions? No? Okay. Well, thanks, Dr. Yang. Appreciate the presentation. This is super interesting. And so yeah, wishing you luck with your continued work on this.
thank you.